Hello. I am Mehrez Karima. Today I will present to you a part of my thesis work entitled Hydrothermal Carbonization of Contaminated Sorghum, Solid Liquid Product Characterization. The presentation is divided into 4 major parts: introduction, after that material and methods. In the third part is the results of the hydroshell production and combustion performance, the liquid phase characterization and environmental consideration, and in the end we have a conclusion and perspectives. But in the beginning, I want to explain the partnership that give the light for this thesis. The first partner is TNO Innovation for Life, which is a Dutch organization for applied research and technology in the Netherlands. At TNO, they develop a spin-off for the hydrothermal carbonization to convert sewage sludge to hydrochar. They pass from the laboratory and pilot scale to commercial product and market introduction. And the second part is ICLOR, which is the Circular Economy and Resource Valorization Research Unit in France. And the thesis was accepted, or it was a part of a gold project, which aims to decontaminate the phytoremediation biomass and convert it into a biofuel. So there are lot of strategy to valorize this contaminated biomass, but I work on this part. So the industrial activity, mining activities, agriculture, urban pollution, and transportation are the main pollution research for the contamination contamination of soil and wastewater by heavy metals. So one of strategy to decontaminate the soil and wastewater is the phytoremediation using hyperaccumulator plants. But these methods can generate a large amount of contaminated biomass, which is harmful for the environment. So the heavy hydrothermal carbonization was proposed to decontaminate this biomass and produce a hydrochar, which can use it as a solid biofuel. But the question here is if this hydrochar can have a good combustion performance and respect the heavy metals limit standard. But we have also the bioproduct, which is a liquid phase, rich in organic matter, and the question also it will be contain heavy metals or not or no. So full characterization and environmental consideration is needed. So for the materials and methods, in this study, we used contaminated sorghum. And if we compare here the concentration of heavy metals in the contaminated sorghum with the biofuel standard, we can see that we can't burn just the contaminated sorghum. So we need to clean it. For the process, in inlet, we have contaminated sorghum and the osmosis water. After that, we put it in the HTC reactor. So the HTC installation is divided into 2 parts. The first part is the hydrothermal reactor, and the second part is the control part, which is characterized with the pressure display and temperature display to control temperature and pressure. For the operating condition, we worked with 4 temperature and 3 time. Always the solvent is osmosis water, and the biomass solvent ratio is 1/10, and the heating rate ranged between 3 and 4 degrees Celsius per minute. In the outlet, we have hydrochar and the liquid phase. So to characterize the hydrochar, so we calculate the mass yield, and we validate the combustion performance And after that, we determine heavy metals. For the liquid phase, we use the total organic carbon to quantify the organic carbon in this liquid phase. And we use inductively coupled plasma atomic emission spectroscopy for the heavy metals determination. And we do some germination tests to evaluate the toxicity of, or the phytotoxicity of this liquid phase. So for the results now, when temperature increased, the mass yield of the hydrochar decreased and the high heating value increased. So to compromise between these two parameters, we choose to work at the temperature between 180 and 200 degrees Celsius. And if we compare here the high heating value of our produced hydrochar in this two temperature with some biofuel standard, we can see that the high heating value of our hydrochar is it's a good. Moving for the combustion performance, so we analyze our hydrochar with the thermogravimetric analysis, and to quantify the overall combustibility of hydrochar, we calculate the comprehensive combustibility index, which link between thermal degradation rate and combustion stability and persistence. So the results in the table, and we can see that the higher comprehensive combustibility index is for the hydrochar produced at 180 and 200 degrees Celsius. So this two temperature can give a good combustion performance for our hydrochar. And to verify now, we can use solid biofuel without verify the heavy metals concentration in this solid biofuel. So I present here the removal efficiency of the heavy metals from hydrochar, and for the optimal condition are 200 and 0.5 and 2 hour for removing to 30 to 60% of heavy metals. So these two conditions are the optimal condition now. But when we compare the concentration of heavy metals in this two hydrochar with the biofuel standard, we can see that cadmium, lead, and zinc have higher concentration compared to the standard. So the operating condition 200 degrees Celsius and 0.5 to hour are not sufficient for effective decontamination of contaminated biomass, contaminated sorghum. Now for the characterization of the liquid phase, so I compare here the concentration of the same heavy metals with the WHO standard, and we can see here that we have 5 heavy metals. They have higher concentration compared to the WHO standard, and also the liquid phase is very has a high level of organic matter also. So we applied some germination tests for this two liquid phase, and we found with raw liquid phase we have germination index 0, and we also applied 2, 5, and 10 dilution, and even with 10 dilution we have just 40% of germination index, which give that the liquid phase is very has a high toxicity, and the post-treatment of HTC liquid phase is crucial for mitigating potential environmental risks. In the conclusion, so the main results is we fixed 2 operating conditions, 200 degrees Celsius and 0.5 hour are identified as optimal, that give good compromise between combustion performance and the heavy metal removal. But we have some limitation. So only 30 to 60% of heavy metal were removed. So we have an incomplete decontamination, and the liquid phase rich in organic matter and heavy metals. So high toxicity, and we should treat it. So the work in progress now is to optimize the HTC, the hydrothermal carbonization with additives such as acid, and test another biomass. We work also on another biomass, hemp, and also develop a sustainable treatment of the liquid phase, such as oxidation, precipitation, coagulation, flocculation, and adsorption. So thank you for your attention.